As you may know, we are very interested in how parts align and interact so as to become larger scale wholes. One place where this becomes really important is the assembly of complex bodies from individual cells, where the dynamics of scaling of goals, from single cell tiny metabolic to grandiose organ or whole body level goals, is a critical set of mechanisms for developing new regenerative medicine. But more broadly, it's also about the multi-scale architectures of mind. How do larger collective intelligences arise, and what policies of their subunits enable the emergence of bigger cognitive light cones? Standard models in economics and game theory seek to model the interactions of a fixed number of individuals competing or cooperating with each other. Their actions control the payoffs they receive, and while their activities can result in rich dynamics within their world, what's normally constant is the identity of the players. In other words, the boundaries between each self and its world are fixed. But perhaps the most interesting part of biology and cognitive science involves processes in which the boundary is changed, when new agents arise, disband, or metamorphose. Biological boundaries are fluid, as we have discussed many times in the context of embryogenesis, evolution, and cancer. It is essential to understand how the boundaries between the self and its world, and the scale of a self and its operational goals, can shrink, grow, and change. A key aspect of biology is the fact that living systems have the agency to drive such plasticity, not merely be the target of it. So, what happens when the choices that agents make actually alter the number, size, and composition of the agents themselves? This forms a fascinating feedback loop, because as soon as an agent does something to change its nature, the entire payoff table can change, because the future self may have very different goals and drives than the former self. By changing that table, which in most studies is a constant feature of the simulated world, this becomes a metasystem where the action of the agents continuously impact the rules of their universe. To get a glimpse into the dynamics of this world, where each agent's decisions have existential impact on it and other future agents, we chose the Prisoner's Dilemma model. But as you will see, to make it relevant to embryogenesis, evolution, cancer, and cognition, we will make a couple of key extensions. Here's Lakshman Srisha to describe the system we built and the data we obtained.
I'd like to talk to you about the work which Mike was talking to you about. It's titled Extending Iterated Spatialized Prisoners Dilemma to Understand Multicellularity, Game Theory with Self-Scaling Players. The lengthy formal title aside, our work is about the Prisoner's Dilemma framework and its extension to try and understand multicellularity in biology. Now, given that we make extensive use of ideas from Prisoner's Dilemma, I'd like to begin by giving you an overview of Prisoner's Dilemma and its variants. So the Prisoner's Dilemma framework, its inception goes back to the 1950s by Merrill Flood and Melvin Drescher at the Rand Corporation. And the framework is essentially about a situation, a hypothetical situation between two players. Let's say it's me and one of my distant Italian cousins, Fat Tony, who also happens to be a mob boss. It's a long story, but on one of these days, well, let's imagine that both of us have been caught gambling by the gendarmerie, and we are dragged by the gendarme to an interrogation room, put in separate rooms, and we are questioned rigorously for our secrets about the mafia and its relationship with gambling. Now, in this peculiar situation that we find ourselves in, I or Fat Tony have two general strategies that we can play. I, for instance, cannot reveal anything. I can keep my mouth shut and I can cooperate with Fat Tony. Or I could just reveal everything. I could reveal details about our business and rat out Fat Tony. And of course, my choices have consequences. So if I don't reveal anything, I just get a year in prison. But if I do reveal everything, I can get off scot-free at the expense of Fat Tony, who ends up spending a 3-year sentence behind bars. Fat Tony has the same two options, and he's faced with the same two penalties. And the interesting thing is, both of us are faced in this situation. And if we put all of our options together in the form of a table, you end up with this picture where both of us can either cooperate with each other or defect on another. And of course, our actions bear consequences. And when you tabulate it this way, you get a a global picture of the situation that you're dealing with respect to each other. This snapshot, this global overview, is nothing but the prisoner's dilemma framework. And it's called a framework because you can use this picture to ask questions such as, okay, what would happen if I cooperated and Fat Tony defected? Or you could ask questions such as, what's the best strategy for both of us where we would get off with the least amount of prison sentence? Now, what's really interesting is that prisoner's dilemma situations, you can encounter them in multiple scenarios over time. For instance, me and Fat Tony could be arrested again next year because, let's say, we're extremely callous. And prisoner's dilemma games doesn't even have to involve a prison. It can be at the restaurant where I refuse to pay the bill and Fat Tony's furious, or it can be at Fat Tony's dasha where he has explicitly forbidden me to buy gifts for his family, but I end up buying gifts anyway. So the thing is, between the same two players, you can have multiple instances of the prisoner's dilemma situation unraveling over time. And because of this involvement of time, both of us can have memories of each other. So I can keep a track of what Fat Tony did to me in past prisoner's dilemma games, and Fat Tony can keep a record of the same. And you can see how we can adjust our strategies. We can take revenge on one another. We can be altruistic with one another. We can form friendly bonds with one another based on our respective memories, based on how we've interacted in the past. Things get a bit more interesting when you involve more than two people. For instance, here's all of these members in our mafia in the group. It involves Kolmogorov, it involves Victor Hugo, it involves our lab director, Michael Levin, it involves my co-authors, Federico and Adam. It's a weird bunch and it's hard to explain, but the point is that iterated prisoner's dilemma games can take place between different players, and it can unravel over time. Generalizing this a bit further, spatialized iterated prisoner's dilemma frameworks, you see them in a lot of societies. You see them in friend groups. You see them in financial markets. And one place which is of particular interest to our lab where you see it is in groups of cells, is in societies of cells. One way you can treat cells is as individual agents, them capable of behaving in a goal-directed manner completely with their own purpose. But something peculiar you notice in biology is the tendency for cells to merge with one another, is their tendency to forego their individuality and combine their goals to that of the collective. You see this in a lot of biological structures because of their morphological organization. Organ systems, for instance, cells of a particular organ, say the heart, are all coordinated towards a single purpose. Cells have differentiated from their individualistic state, and they've kind of joined forces towards a common goal. And this merge tendency is something you see distinctively in biology. Another area where you see this ability to merge is in financial markets. Here, for instance, is a tiny sector of the technological market. And you can see major players here. You have IBM, you have Lockheed. And let's, for instance, consider two startups, Cray and FET, occupying a certain percentage of the market. Now, there could occur a situation when both these startups, Cray and FET, merge with Lockheed because of a merger. There could also be a situation where the merger fails with Cray and Cray ends up splitting with Lockheed. So these behaviors of merging and splitting is still unique between players, but is not explicitly captured by the prisoner's dilemma framework. And when you think about it, a lot of complex systems exhibit this tendency, the tendency to merge as well as split. Like I said, the traditional prisoner's dilemma framework gives players the option to just cooperate or defect. But what we observe is that game dynamics or the dynamic of a complex system can change significantly because of agents' ability to merge as well as split. So to account for this, we extend the prisoner's dilemma framework by introducing these two additional actions, the merge action as well as the split action. Now, because of this, players not only have the option to cooperate individually with one another by having their own goals, but they can forego their individuality by merging with one another, following the behavior or the goal directed or the goals of another agent. I'll get to the boring parts later, but one of the most interesting things that I'd like to show you is the simulation which results out of this new framework. And here's such a simulation. So the grid that you see here is composed of a lot of agents. The square grid is composed of a lot of individual sub-agents whose individuality is unique. The color code is an indication of the sizes of agents which are present at any point in simulation. So here's how the simulation looks when you run it over multiple games. Larger agents keep popping up, indicated by their color codes. Some agents choose to merge, other agents choose to split, because of which they can increase their sizes or they can decrease their sizes. You can see a lot of arms popping up from some of these tissues, and there is general topological or morphological structure to many of these merged agents. As simulation proceeds, you notice that things are getting complicated. Rather than a bias towards splitting, there seems to be an almost impartial bias towards merging, even though we don't give such a bias in our framework. It's almost as if agents aggressively merge towards larger and larger and larger clusters. If you extrapolate this dynamic, you can come to imagine that eventually every single agent would have merged into a single global singular agent, we'll call it. And it's there it is. This is the singular agent. This is not the only interesting thing throughout the simulation. There were several parts which we'd like to take you through. But I'd like to show you what exactly happens in each and every single game. Okay, so let's roll back everything to the start, where we once again have this square grid composed of several agents. To help you differentiate all these subagents, let me draw a grid. So each subcell in this grid is representative of an agent. And they're all unique. They have their own way of behaving, they have their own goals. So the way a game begins is an agent is picked at random in this world. And let's say we pick this particular agent here, and we'll also consider its neighboring area, its neighboring agents. And here's how that looks up close. Here's a zoomed in picture of that. So you have the selected agent, which is highlighted in blue, agent number 8, and it has these surrounding neighbors which it has. Now, this chosen agent can play a game of merge-based prisoner dilemma with any of its neighbors. It has no restriction as such, and usually one of these neighbors is chosen at random. So let's say agent number 25 is picked at random as its opponent, and now a game begins between agent 8 and agent 25. So what exactly happens during the game? So here's how a gameplay rolls out. So once agents have been selected, once an agent has been selected and its opponent has been chosen, agents first fetch their memory. Now, this is probably a good time to mention that we treat our agents as reinforcement learning agents. And they carry two main things. They carry a list of memories, which is essentially a list of the past actions that they've played. And they also carry a policy table, which tells them how to behave. So let's take this step by step, and let's just think about the memory, for instance. So as soon as agents are chosen to play, they consult their memory to, to, to get a representation of what has happened before. So let's say that agent 8 has the actions defect stored thrice in its memory, and the And the orange agent number 25 has stored cooperate defect, merge cooperate defect as its actions. So they're different in length. And what agents immediately do is they construct a memory representation from these memories that they have, just for them to have an idea of what has happened before, in order to assess them to act in this current situation. Of course, this is the initial game, so technically agents shouldn't have any memory stored, but let's assume that we're considering a hypothetical situation and that they actually do have some action stored. So they have this memory representation, and what happens next? This memory representation is now used to sample from a policy table. Like I mentioned before, agents carry a policy, which is simply a mapping from states to actions, a mapping from memory states to action probabilities. And every agent maintains one. And let's hypothetically consider that these are the policy tables of agent 8 and agent 25. So the way an action is chosen is by simply picking the action which has the highest probability for that particular memory state. So notice the memory state for the blue agent gives rise to a defect as the highest probability action. And for agent number 25, the beige or the orange colored agent, you have cooperate as the action with the highest probability. So agent 8 and agent 25, they both play their hand. They say, okay, defect is the correct action to play here, and agent 25 says cooperate is the correct action to play here. And based on their actions, this is just the same slide with their corresponding actions, they receive a payoff score, and they receive a payoff score based on the pre-made payoff table, which I showed you initially. This is, of course, predefined and it's static. So the agents receive scores based on this payoff table, and they use these scores as feedback to update their policy using the Q-learning algorithm. And they also update their memories based on the actions that they've played. Now, this is all well and good, and this kind of represents the classic prisoner's dilemma. So what's different in this merge or split based setup? Now, imagine, for instance, that using the memory representations, these agents pick the merge action instead of either cooperate or defect. So let's say that the highest probability action is merge based on their memory representation. And as usual, these agents receive a payoff score, and they use the payoff score to update their policy table. But something else happens, something which changes the game board itself, the anatomical organization of these agents itself. And this is the merge action. Essentially, a merge means what it implies. These two agents coalesce into a new agent. A new agent, agent 401, is created, and it derives its policy and its memories from its best constituent. So whichever is performing better, agent 8 or 25. It receives their memories and their policies, and it becomes this independent entity. And this independence is represented in the board state, spatially represented in the board state, because this coalesced agent now occupies both their positions in the board. And this is how it looks in the actual simulation as such. So you notice these two agents having merged together to form a new agent of size 2, and you notice their spatial boundaries have been coalesced. So that is about merge, but there is also another operator, which is the split operator. Let's imagine that a few games have already been played, and after the nth game, agent 401, this new agent, this new merged agent, chooses to play a new game with its neighbor, agent 11. And once again, both of them fetch their memory representations and they use their policy tables. And let's assume that this particular memory representation that they have forces them to choose the split action. Now, as usual, the split action also bears a corresponding payoff score in the payoff table. So each agent receives a payoff score, and they use it to update their policy as well as their memories. But once again, there is a spatial reorganization when agents choose the split action. Specifically, the agent, this qualist agent, agent 401, splits back into it splits back into its constituents, which is agent 8 and agent 25. And both these constituents, they inherit the policy and the memories of the combined agent. And this essentially is the split dynamic. Now, given that you know how merges and splits work, here's how the simulation looks with some grid lines drawn to help you count agents and their tendency to form these clumps together. Of course, I won't go through each and every frame. I'll pause it here for a minute and I'll come back to the simulation later. But for now, I'd like to bring your attention back to the question of how can we study these simulation dynamics? We have all of this structure popping up. And what are the interesting things for us to monitor and understand? And one thing is the concept of memory size. Something I didn't mention while I was explaining these dynamics was that while agents build their memory representations, they're constrained by their memory capacity. Agents carry a hyperparameter which decides the amount of memory that they can carry. For instance, the blue agent here has a capacity of carrying only 3 actions, whereas the beige or the orange agent has the capacity to carry 5 different actions. And you can imagine that this tendency to remember more or less of the past influences the representations that they have in the present, and in turn influences the actions that they can take from this particular state. And this is what we find really interesting, because we want to ask, how does this capability of agents to remember more or less of the past influence the simulation dynamics that we observe? To measure this, what we did was quite simple. So we had a simulation, we set up a simulation where each and every agent was fixed with a constant memory size, say 2 in this case. And as simulation progressed, we monitored the average sizes of these agents. So here's, for example, how such a plot could look. And of course, since we are trying to understand the influence of memory size on these merge dynamics, we initialized multiple instances of the same simulation, but at different memory sizes. So in one particular simulation, we had a number of agents with a constant memory size of 1, a separate simulation where agents had a constant memory size of 2, another experiment where we had agents with a memory size of 3, and finally a simulation with a memory size of 4. And in each of these, we monitored their average tissue size as simulation progressed. And here's how that dynamic kind of correlates. There's a lot going on in this frame. I'd like to skip to the end of these simulations and just show you these graphs. So here's all of these graphs put side by side together, and each panel is representative of simulations run with a particular memory capacity or memory length. And the panels represent average tissue size over time. So notice that for simulations with a memory size of 1, the average tissue size rises to a maximum of 15 and then stabilizes to around a value of 5. But for memory sizes greater than 1, for memory sizes of 2, 3, and 4, you have a sort of aggression towards merging. Agents rapidly combine together to form this single merged entity, which I described. And just to get you back, here's how that singular agent looks. So towards the end of simulation, you have this single merge cluster which pops up, and this is what we term the unified agent. And another interesting thing you observe in these graphs, in these high memory graphs, in memory sizes 2, 3, and 4, is the tendency for the memory size to stabilize at different points and then rise sharply. Moments of stability followed by sharp rises. And this kind of equilibrium followed by rises is peculiar because we don't have an explanation for it, but we nonetheless notice it reliably across memory sizes. Now, a second thing we wanted to check at different memory sizes was the fitness of agents, especially their payoff scores. at any particular situation in time, you have a variety of agents in the world. For instance, you have agents with sizes ranging from 1 to 30 in this particular game step. And what we decided was to group these different agents into two major groups. And these groups were the unicellular tissue groups and the multicellular tissue groups. Unicellulars, of course, were agents which had a size of 1, and multicellulars were those which had agent sizes 2, 3, and upwards, anything greater than 1. So you had these two different factions, unicellular tissues and multicellular tissues, and we wanted to understand how their fitness varies over time. We wanted to understand how their fitness fluctuates over time as simulation proceeds. And this is how a graph like that could look. But of course, like I'd mentioned, we want to ask this question at different memory sizes. So once again, we had 4 different simulations where agents were initialized with a constant memory size and recorded their fitnesses. I'd like to simplify this simulation as before by only retaining the graphs. And this is how that picture looks. As before, each panel is representative of a simulation run with a specific memory length. And each graph is a plot of the fitness over time for unicellular groups as well as multicellular groups. And I'd like to clarify what I mean by fitness here. Fitness is simply the time averaged payoff scores which agents receive as they play iterated prisoners dilemma games, merge based iterated prisoners dilemma games. And what we notice from these graphs is that across all memory sizes, across memory size 1, 2, 3, and 4, multicellular groups have a higher fitness score than unicellular groups. They tend to perform better than unicellular tissues, implying that there is an advantage towards multicellularity even when you don't explicitly give it through your framework. Another interesting thing that you can notice is that in memory sizes of 2, 3, and 4, the fitness after a certain moment drops. But we don't understand why multicellular groups perform better than unicellular groups. One thing we do understand is the reliable drop in fitness and their eventual convergence as they approach the unified agent status. And this has to do with the merge and split dynamic, especially the merge dynamic, because during the later stages of simulation, there are not many agents to play iterated prisoners dilemma games with. So fewer agents to play against with is one contributing factor. And the second contributing factor is that the merge action carries a payoff score of 0. The tendency is for their average score to drop because they keep accumulating zeros. So these two dynamics, the presence of fewer and fewer agents as agents choose to merge, combined with the tendency of merge actions to carry a 0 payoff score, eventually reduce both of these groups to a fitness of 0. Next, we studied the cooperation tendency of multicellular and unicellular agents. Once again, just to recall, at any state in the game, you will find agents which can be grouped into 2 major sections, the unicellular tissue section or the multicellular tissue section. And something you can ask is the proportion of multicellular groups cooperating with their neighbors and the proportion of unicellular groups cooperating with their neighbors. And by cooperating, I mean explicitly choosing the cooperate action with their neighbors when they're playing iterated prisoners dilemma games. As usual, you can track the percentage of agents cooperating in each of these major tissue groups, and you can end up with graphs looking like this. But as before, we'd like to understand cooperation as a function of memory size. So we have multiple simulations where agents have a fixed memory size, and we monitor the percentages of these 2 tissue groups cooperating in each. And this is how that simulation plays out. As before, I'd like to skip ahead and just simplify these results to just the graphs. And here's how that looks. Each panel, once again, is a particular simulation run with a specific memory capacity. And each panel is a graph of the percentage cooperating, the percentage of multicellular or unicellular tissues cooperating over time. The general observation that you can make is that there is no difference in the cooperation tendency between unicellular and multicellular tissues. And one reason could be because both these tissue groups don't choose the cooperate action as frequently as they do merge. Before they can cooperate sufficiently, they've been merged into a different cluster, and you end up with absolutely no difference between large sized tissues as well as small sized tissues. This is perhaps my favorite part of the results section, and it has to do with the simulation I showed you at the very beginning. It's a spatial visualization of our simulation as agents play games of merge-based iterated prisoner's dilemma. And you can't help but feel intuitively that there is some sort of structure arising here, that it isn't just random, that there is actually some sort of structure being popped up. Let me fast forward a bit and pause. And in this particular snapshot, you notice once again a lot of different tissues with a lot of different shapes. You have tissues of size 1 all the way to 13, and all of these tissues have different shapes. And one particular thing that we wanted to ask was their spatial relationship with each other. For instance, we wanted to ask, what is the probability of finding a tissue of, say, some size X next to another tissue of size Y? For instance, what's the probability of you finding this tissue of size 5 close to another tissue of size 7 or even 1? The result of that visualization is simply this heat map. This heat map is a description of the probability of finding a tissue of size X next to a tissue of size Y. The pattern you notice is that irrespective of the tissue sizes ranging from 1 to 397, you will find tissues in the range of 1 to say 100 close to them at any point in simulation. And I'd like you to just think about this, because here's the simulation once again, and let me just pause here. Let me just pause at game number 26. The implication that small sized tissues can be found close to any other tissue is the blurring of agential boundaries. Specifically, I'd like you to look at this particular agent. It doesn't look like it's an agent with a size of 2 as indicated by its color code. And this is because it isn't. It actually is a set of 2 size 2 tissues placed close to one another. And this proximal organization completely blurs their boundaries. And this keeps on occurring at various stages in simulation. For instance, here's the color green indicating a size of 3, and you notice long taped structures which are clearly not agents of size 3, but multiple size 3 agents placed close to one another. The tendency for these large agents to show up has always been fascinating to us, because it reminds us of a complex system, and something reminiscent and something which has become a cliche in complex system is that the collective behaves in a different manner than the sum of its parts. And we wanted to check if this characterization holds in our setup as well. So we asked this question: are larger agents better integrated with their environment? In the sense, do larger agents change the dynamics of the game, change the future dynamics of the game in a different way than if they were just unmerged parts? To quantify this, we used an arcane metric in information theory known as the integrated information metric, or phi-R for short. The formula might be daunting, but I'd like to break it down bit by bit by considering a particular instance during simulation, say game number 174, during which the spatial distribution looks as so. Let's focus our attention on this particular agent which has a size of 5, and let's not only look at it but also its neighbors as marked by this black boundary. Given our focus on this particular section, we can now dissect the phi-R metric. AN here stands for an agent. It can be any agent in the board state. And since we have chosen to focus on an agent of size phi, AN here simply stands for, is representative of this particular agent. Similarly, EN stands for the neighbors of this chosen agent of size phi. And the neighbors, of course, are all of its surrounding agents, which is composed of agents of size 1 as well as this green agent of size 3. And finally, XN is a representative of the entire thing, of not only the agent, but also its neighbors. And I here is simply the mutual information metric of the actions taken by each of these agent groups that we have considered. It's simply the mutual information metric at the current time step and the future time step. If you put all of these together, what the phi-r metric intuitively is computing is the difference in the mutual information that the whole carries about its future as compared to the parts carry about their future. You can imagine that a positive phi-r value indicates that the whole is actually more informative. It actually carries more information about the future than either of its parts, as a result of which it is better integrated with the environment and behaves like a complex system. This is our result, and the graph is a plot of phi-r, which is the integrated information metric, which I just discussed, as a function of tissue size. What you notice is that as agents' size increase, there is an increase in their fluctuation. And when you try to fit a regression line to this data, to this fluctuating data, you end up with this red line, which has a positive slope. And the positive slope is in a nutshell indicating that there is this mild increase. There is a mild increase in phi-r as agents' tissue size increases. This is exactly as if the larger an agent becomes, the more it behaves like a complex system, influencing the future of the game to a greater extent than its individualistic parts. Finally, I'd like to talk to you about boundaries and agents. How do you recognize an agent? Do you attribute agency to any entity which has physical structure to it? Do you attribute agency to me because you can see me speak and you can notice that I have physical structure? Is that how you quantify an agent? And if you say yes, that's totally fine, because that's how we've been visualizing agents so far. In all of our simulations, we've been color coding agents by their size, their anatomical boundaries, and we've been observing how they evolve over time. And they indeed are agents, so it's totally fine to call them or treat them as such. But what if instead of visualizing their anatomical boundaries, we visualized their behaviors? We color coded all of these agents by the strategies, the actions, or the behaviors that they exhibit during games of Iterated Prisoners Dilemma. Here, for instance, is how one such simulation looks. And mind you, these simulations are identical. It's just that we've changed the color coding. So what you notice on the rightmost panel are agents which are color coded based on strategies. And the color bar on the right doesn't exhaustively list every possible strategy. It lists only the top 5 strategy based on how popular they are at any particular time. X here denotes the strategy. X here denotes that many agents haven't played a game. But otherwise, you notice a lot of patterns popping up. Now, at first glance, you might think that there's not a lot of difference between visualizing anatomical boundaries or behavioral boundaries. Of course, you see similar kinds of shapes being popped up. So you might think that there's not a lot of difference. But you'd realize how wrong you were when if I synchronize both of these and then play them back to you. Notice that they are in sync now, and the behavioral boundaries are much more complex than the anatomical boundaries. And the complexity only explodes as the simulation proceeds. I'll pause these simulations here so that we can ponder about this for a moment. What this implies is that the agency that you attribute to an agent depends upon you as an observer. Based on the observable that you as a third person have access to, you tend to treat agents in different ways. For instance, if I showed you just anatomical boundaries, agents with anatomical boundaries, you would attribute some form of complexity to them. But if I showed you behavioral boundaries, you would attribute a different form of complexity to them. The point is, based on what you see, you tend to change your perception of how complex this agent is. And this is really interesting because it asks us to be mindful about treating agents only as those which have physical morphological boundaries. And it encourages you to treat even patterns as agents, even behavioral structures as agents. The question we asked here was the dependence of these two attributes. Does anatomy tend to cause behavior, or does behavioral strategies tend to influence anatomical boundaries? This causal dependence was something that we were interested in, and the way we quantified it was using a tool from information theory known as the transfer entropy. Intuitively, the transfer entropy from a sequence X to a sequence Y is the reduction in the uncertainty of future values of Y when you have access to the past values of both X and Y. So all that it means is the amount of information X contributes to the future dynamics or the future values of Y. And of course, the sequence X and the sequence Y corresponds to anatomical sequences or behavioral sequences. So for every agent in the grid, we collected a list of their sizes throughout simulation and a list of their strategies throughout simulation, and we computed their transfer entropy. We compute the transfer entropy for each and every agent in the two-dimensional grid. And you can imagine that at the end of computation, you would have a bunch of transfer entropy values spread around throughout the grid. To report it in a concise manner, we average all of them spatially, and we report a single value, and let's say it's 1.2 nats. An interesting parameter in the transfer entropy is the lag period. The transfer entropy computes the reduction in uncertainty of the future given the past from a sequence X and a sequence Y. The duration of the past that you account for is given by this lag period. So for a lag period of 1, this could be the value. We also computed for other lag periods. And you can imagine computing transfer entropy for a number of lag durations for sequences of anatomy to behavior as well as behavior to anatomy. And here's how that graph looks. X-axis here is the lag duration ranging all the way from 1 to 120 time steps in the past. And the Y-axis denotes the transfer entropy. You notice two major trends here. One is the red graph and the other is the blue graph. The red denotes transfer entropy computed from anatomy to behavior, and the blue graph denotes transfer entropy computed from behavior to anatomy. So we measure causality both ways in both directions over multiple lag durations. What you can observe is that across multiple lag durations, anatomy influences behavior to a higher extent than the reciprocal relationship. There are other interesting parts to this. We mentioned several in the paper. One I'd like to bring attention to is the transfer entropy of behavior to anatomy reduces below 0 for lag durations between 20 and 60. It means that in fact, behavior can hinder the causality of anatomy. All right, so those were some of our results. And if you take them seriously, they have a few implications which I'd like to talk about. The first is that agents with larger memories aren't necessarily better than agents with smaller memories. Here's a graph from before where each panel denotes simulations run with a particular memory capacity. And notice that in all 4 panels, despite increasing the memory size, the maximum fitness of these unicellular groups or multicellular groups, it remains below 10. It barely reaches 10, and memory size has absolutely no impact on giving a fitness boost to agents. So larger memories aren't necessarily better than smaller ones. A second implication is that when you run simulations where agents have a memory size greater than 1, they tend to aggressively merge into a single agent. Here's once again a graph which I showed you before. It is a plot of the average tissue size versus time for simulations initialized with different memory sizes. And notice that when memory sizes are greater than 1, for memory sizes 2, 3, and 4, a unified agent naturally emerges. Another implication was large agents don't necessarily cooperate any better. So multicellular agents and unicellular agents, they cooperate identically. Here's a panel from before showing you the cooperation tendency of each of these clusters in simulations initialized with different memory sizes. And you notice both these tissue groups cooperating identically The implication is that becoming large doesn't necessarily make you cooperate any better with your neighbors. Another thing which we observed was that larger agents distinctively control the future dynamics than their individual subparts. It's as if the larger an agent becomes, the more similar to a complex system it behaves. Of course, in the sense that its whole behaves in a completely different way than the sum of its parts. One fascinating thing which we observed was the emergence of distinct topological structures throughout our simulation. And it turns out that there is some sort of structure to this. Smaller or medium-sized tissues are found close to any other tissue at any point in time during simulation. Finally, you can attribute agential behavior, or you can identify agents in multiple subspaces. You can identify it in anatomies, or you can identify it in behaviors. And the conventional notion that agents are those entities which are separated from their environment doesn't necessarily have to be true. It is totally contingent upon you as an observer and the kind of observables that you have access to. If I showed you anatomical boundaries of an agent, you would call that an agent. If I took you to the space of behaviors and if I showed you behavioral patterns, you would attribute those as agents. Similarly, you can seep into morphological spaces, you can seep into physiological spaces, you can seep into chemical spaces. And based on the space that you are in and based on the observable you have access to in that space, your concept of an agent can change. Your concept of how complex an agent is can change. I hope this illustration kind of serves as proof for that purpose. So that was our work. I'd like to end by introducing a few people who were instrumental in this work coming together and even giving you some perspective about how the ideas were incepted and how they came into being. It was Mike who came up with this idea of extending Prisoner's Dilemma to include these actions of merge and split to try and explain perhaps multicellularity in biology. Peter Smile, he built the very first model of this iterated Prisoner's Dilemma framework. I came apart and extended it later on. Once we had most of our results, a couple of months later, we were wondering about this ability for larger clusters to behave in a different way than their individual components. And this was when Federico helped us in quantifying the integrated information metric. Another person was Adam Goldstein. We'd sent him the paper initially for some comments, but he was generous to understand some parts of the paper which we didn't ourselves. The current state of the work that you find it in is mostly because of Adam's comments and his ability to chisel down on some of the problems that we had. These were not the only people involved. I have a lot many more people to thank from the computational group and the Levin lab. Joel for his comments and Torch for sending us some of his emails. Hananel and Ben for their comments as well. And finally, Julia for helping us put together the manuscript. Well, that's it. I'd like to leave you there. If you have anything to tell us about, anything to discuss, please write to us. If you're interested in the code for this project, it's open source. You can find it on GitHub, QR code to help you find it. So that's it. Thanks.